Now I want to work a problem as an example of the Chapter 25 electric potential situation. I want to work a classic problem where you're given some sort of a symmetrical distribution of charge and you're asked to find the E field in all regions of space and the electrostatic potential field in all regions of space with some place defined for V being defined as 0. If it's spherically symmetric, that's typically infinity. If it's cylindrically symmetric, it's one of the surfaces of cylindrical symmetry that's grounded. So, for example, let's look at problem 68 of the 9th edition. It's a Geiger-Mueller tube radiation detector, and a picture like this. It's a right circular cylinder. The inside is positively charged, this here. So it effectively has some lambda charge per unit length on it. It's called the anode. And then out here is negatively charged, negative lambda charge per unit length on that. It's essentially, we're going to assume cylindrical symmetry, so it's for all practical purposes infinitely long. So we can employ our spherical symmetry. And the inner radius of the anode is RB. And the radius here for the cathode is RA. And you're asked to find the electric field in this region. In particular, you're asked to find what the potential difference is between the cathode and the anode. So you need to get your E field in there and then do, E dot ds, integrate radially, and get the delta V. So let's do that. First thing you have to do, if you want to use Gauss's law to get the E field in this region here, then that's where you have to draw your Gaussian surface. Radius R, where R is greater than RB but less than RA, obviously. And now you have to write what I told you before. Whenever you have your symmetry, you have to identify the symmetry, state it, and say by, in this case, cylindrical. So you would say by cylindrical symmetry and Gauss's, too many S's there, and Gauss's law. E equals ER is a function of R hat, where this is the radial coordinate and cylindrical coordinates along the axis of symmetry, orthogonal to the axis of symmetry. And this function ER of R, this radial function, is Q enclosed divided by 2 pi epsilon naught R L. Okay, so that would be your starting point. And any problem where you're going to use Gauss's law to get the E field. State the symmetry that you have identified, and that by Gauss's law on that symmetry, give the functional form of the E field that you know must obtain. Then you pick a Gaussian surface over which that E field you know is a constant, even though you don't know its exact functional form, because you know its symmetry, you know it's a constant over that Gaussian surface. So it comes out of the integral for the flux E dot dA, and then you can just do E times A, right? Electric field over the area through which you have an electric flux, and then that equals the Q enclosed. Again, you don't have flux through the end caps of your cylindrical Gaussian surface, as we showed when we derived this stuff. So all you have to do is get the Q enclosed. This Gaussian surface here, it's got a cross section. I'm not showing this dimension coming in and out of the board, and that's where you have your length L. So how much charge is enclosed by that Gaussian surface? Radius little r. Well, as long as r is greater than RB, then it's enclosed in that lambda charge per unit length along the axis of symmetry, but not the minus lambda outside if you're less than RA. And that's where we're going to be at. So we just end up with Q enclosed equals lambda L, charge per length, times the length of our Gaussian surface. And that will go in here. And so our functional form for the E field is lambda divided by 2 pi epsilon naught r. And the L cancels out. It always has to be the case, remember, as I told you before, it always has to be the case that Q enclosed, when you have cylindrical symmetry, is proportional to the length of the Gaussian surface L, because that's just absolutely arbitrary. And that will have to cancel out. And so there's your lambda. Now, let's do our integral. We get delta V. Delta V. We'll integrate from RB to RA minus E dot ds. Now remember, it's independent of the path, so let's be wise in how we choose our path. Our E field is strictly radial, so let's just choose a radial path, right? This dot product is very simple. So you just choose ds is just dr r hat. Then when you dot these two guys, you get r hat dot r hat is 1, and you just have this radial function E, dr, and anti-differentiate, evaluate. No problem. Get rid of that. Alright, so delta V equals minus integral RB to RA of lambda over 2 pi epsilon naught r dr equals, you just have dr over r, which is the natural log, minus lambda 2 pi epsilon naught natural log RA over RB. And then the minus sign, can you go in here and flip this? But typically all you're interested in, whether or not you get plus or minus, just has to do with whether or not you take the leads of your voltmeter and flip them, right? 2 volts reading one way, and you flip the leads of your voltmeter, gives you minus 2 volts the other way. So typically all they're asking for when they want to know what the potential difference is they want to know absolute value of the potential difference. And so that's why the answer given in the book, it drops the minus sign there. It's lambda over 2 pi epsilon naught natural log RA over RB.